Math 2413, section 10.7, vector functions. In this video, or series of videos, we're going to introduce the concept of a vector function and do a little bit of calculus to it. Most of the calculus you're going to see is stuff that you already know. Derivatives, derivative rules, integrals, limits, etc. But before we do any of that, let's just introduce what vector functions are and introduce some of the terminology. A vector function is a function whose domain is a set of real numbers. So it takes in a single real number value and whose range is a set of vectors in Rn for some natural number n. In other words, its output is a vector. The size of the vector depends upon the function. It can be an R2, such as this one. It can be an R3. It can be an R whatever. But its outputs are always vectors from the same space. For example, let's take a look at this vector function. And you can usually spot a vector function, especially when I write them, because I'll write the vector arrow over the function name to indicate that the output is a function. In the textbook, it would be written in bold font, but I like to write the vector arrows because I have trouble writing on a board and making it look bold. In this particular vector function, we have r of t is equal to the vector whose first component is t minus 1 and whose second component is t minus 2. These two functions that make up the components are appropriately enough called component functions. Component functions. And we can also write them individually by saying that, I'm going to use the same notation as the textbook, saying that x is equal to f of t, which in this case would be t minus 1, and y is equal to g of t, which is equal to t squared. But generically speaking, we can call the first vector function some function of t, the first component function some function of t, the second component function some function of t, or whatever the parameter is, whatever the input is. And if there were a third component, we could call it h of t. But the functions that make the components of the vector function are called component functions. We're going to be doing several things with these, but before we start calculus, I want to briefly show you how to take a vector function and sketch a graph of it. Now technically the outputs are vectors, but we can represent them as points that are endpoints of vectors whose initial points are at the origin. So for example, if we wanted to sketch a graph of this, we could start by choosing some values for the parameter. Let's start with some pretty straightforward values. Let's go between -3 and +3. Now, how do you know which values to pick? Honestly, you don't. We're just picking some numbers at random and hope that some pattern emerges. And let's see what r of t is going to look like. Now, you can calculate each vector's components one at a time, or you can calculate all of the first components and then all of the second components. Depending upon the caliber of the functions, I would go one component at a time so that I'm not shifting back and forth between doing this function and then that function. For the first components, all I have to do is take the input and subtract 1. So if my inputs are -3 to 3 and I subtract 1, then my first components will be -3 minus 1 is -4, -2 minus 1 is -3, and so on. For the second components, it says to square the input, so all I have to do is square these numbers. 9, 4, 1, 0, 1, 4, 9. And here's a table of outputs for this vector function. If I wanted to sketch this graph, well, first off, I need an x and a y axis because this is a vector in R2. We only have x components and y components. Secondly, looking at my vectors, my x's ended up being between -4 and 2, so I need to go back 4 spaces on the x-axis, but only 2 to the right. And my y components go between 0 and 9. So I don't need any space down here, so I'm going to reset this so I have more space on the positive y-axis. 1, 2, 3, 4, 1, 2. But my y components go all the way up to 9. 2, 3, 4, 5, 6, 7, 8, 9. All right, let's see what these vectors look like. When t equals 3, I'm at the vector negative 4, comma 9. The point negative 4, comma 9 is up here. As a vector, it would be the vector whose initial point is the origin. And, well, let me try that again. How about I get a straight edge? What a novel idea. The point negative 4, 9 can help us locate the vector negative 4, 9. So that vector represents r of negative 3. Remember, that was the input that produced this vector. And if we were to graph the rest of them, the next output is negative 3, 4. So negative 3 up 1, 2, 3, 4. So about here. And if I connect those, then that represents the vector r of negative 2. It's going to get a little crowded in here. When t was negative 1, my vector was negative 2, comma 1, which is just right there as an ordered pair, but as a vector, looks like that. So that vector is r of negative 1. And then when I put in 0, the vector that I got out was negative 1, 0. So if I go to negative 1, 0 and draw the vector from the origin, then that little arrow right there is r of 0. Let's put the rest of them up here fairly quickly. 0, 1 is the next vector, so sort of a wider set. I connect that from the origin. That would represent r of 1. And then r of 2 is 1, comma 4, so over 1 up 4. I connect those. That's r of 2. And then finally, when my t was 3, my output was 2, 9, so I get a vector way up here. Or rather, I get a point way up here that I make a vector by connecting it to the origin as its initial point. Now, that's a lot of stuff to draw. However, when you graph a vector function, you actually don't have to draw all vectors. The presumption is that the vectors on the graph of the vector function are all originating from the origin, so really all we have to keep track of are the terminal points of those vectors. And it probably won't surprise you that these make a parabola. We'll see why in just a second. So when you draw the graph of a vector function, you don't have to actually draw vectors like I did in red. You can just draw the endpoints of those vectors by thinking of these vectors as ordered pairs and then connecting them, like regular graphing. But unlike regular graphing, number one, this isn't called a graph, this is called a space curve. Normally we call them space curves when they're in 3 dimensions, but technically it doesn't matter the number of dimensions, it's called a space curve. Secondly, the order in which this space curve is drawn out is not just random. For example, we don't just trace it out left to right or right to left. The order that it's traced out is determined by the order of the t values that generated these points. For example, the least t value that we had was -3. So I'm grabbing a different colored marker. I'll grab this blue marker. So this point here was t equals -3. Think of it as a time. Think of t as measuring time. I know, how do we have negative time? Well, we take a point in time and go back 3 seconds and say this is where it was 3 seconds before the beginning. And then here was when t equals -2. And then t equals -1 was right here. T equals 0 is down here at the vertex. T equals 1 was right there. T equals 2 is right there. And t equals 3 is right here. And it's not uncommon to actually label points on a space curve based on the value of the input that got us there. Almost like a timer. T equals -3, -2, -1, 0, 1, 2, 3. And a space curve has what's called an orientation. The orientation is the direction the curve is drawn out as the parameter's value increases. In other words, as the t got greater and greater, where were the points going? You usually represent the orientation of a curve with arrows on the curve pointing in the direction. Now this is just a big old sloppy mess. At this point, I'm regretting drawing all the red vectors. So if you'll allow me to just for a second, I'm going to erase this and quickly redraw it, not as accurately. I kind of remember how it went. Like that. And we had points where t was -3, t was -2, t equals -1, t equals 0 down here at the bottom. I remember t equals 1 was the y-intercept, t equals 2 was up here, and then t equals 3 was just as high as t equals -3. So by keeping track of the value of the parameter, the values of the inputs that generated these vectors, and more specifically these vectors' terminal points, then I can denote the orientation by drawing an arrow between each of the time intervals. And honestly, it's not necessary to put one arrow between each time interval, -3 to -2, -2 to -1, and so on and so forth. But doing that actually illustrates the speed at which this point would be moving. Think of this as a particle moving through space, and this function telling you where it is at a certain moment in time. It only took 1 second to get from here to here, but another second to travel the smaller distance, and another second to travel even the smaller distance. So it seems like it's slowing down. But as it turns around, over 1 second time intervals, it travels this far, and then a little farther, and then a lot farther. And so it's speeding up because it's covering more distance, but in the same amount of time. So there's a lot of information you can glean about the path of an object if its path is defined by a vector function, and you can document where you are on this path at certain moments in time. There's one more thing I'd like to do with this, but I'm not sure how long this video has been running. I don't want to make it too long of a video. Yeah, it's already past the 10-minute mark. So I'll start another video to show you what I want to do with this next.